This is lesson 14. In this lesson, we'll be talking about the mark control module. The mark control is made up of two modules, the receive and the transmit module. You can find this the verilog code at projectfpga.com/tcp select the mark control module. So this is the mark control made up of the transmit and the receive module. Select the transmit control. So this mark control module is used during when the transmitter operates in full duplex mode. Full duplex means it's transmitting and equally receiving at the same time. So this module does what we call flow control. Flow control. What is flow control? We use flow control. Let's take in an instance where the receiver is busy and the transmitter keeps sending in more and more data. So the receiver can equally send a signal to the transmitter telling the transmitter that, hey, hold on, I'm very busy. But in half duplex mode, the receiver keeps receiving, so it cannot send a feedback to the transmitter. So that's why this module works only in full duplex mode. Therefore, in this mode works. This mode we be using. So in a situation whereby the receiver has much data is receiving, it sends this signal. We call it pulse control frame, or simply control frame, or you can call it a pulse. It sends it to the transmitter, telling the transmitter to pause, stop sending, I'm busy, or I have much data to receive. So the first mode we'll be talking about is the transmit control. This transmit control is used by the receiver. This module, this transmit control circuit, belongs to the receiver. The receiver uses this module or sub-circuit to send the message to the transmitter, telling it to wait. So while the transmitter is sending to the receiver will now send back to the transmitter, telling it to pause for a while. So now this is how this transmit module works. So for the receiver to use this module, it has to set this signal in the register. This TX flow signal has to be set in the register. TX flow has to be set in the register, and then if need arises to send this control frame, is going to assert this signal TS pause request. So assuming the receiver has much data to receive and it asserts this TS pause request without setting this TS flow signal in the register, the control frame is not going to be sent. And assuming it sets this TS flow in the register and it doesn't request for this pause control frame to be sent, the transmit module won't go. So these two signals are very compulsory. One needs to be set in the register and one is used during operation to say, oh, stop. So the first signal output is this will send control frame, is the first signal the receiver asserts. So but here you'll be seeing a lot of TS control, block TS use data in, TS use data out, TS done, TS start from, TS about, but they all belong to the receiver. It doesn't really mean it belongs to the transmitter. So this is the receiver's transmitter that owns this circuit, the transmitter of the receiver, and not the main transmitter sending the data. So the receiver's transmitter will send this pulse because it's working in a full duplex mode. It can also transmit at the same time. So it first of all asserts this will send control frame. So how does this will send control frame turn on? It turns on from here. it, as I told you earlier, the TS post request and the TS flow. So I would like to simulate this circuit actually by, let me add my clock. I see I'm adding my clock tick enable. So whenever the receiver's transmitter accepts these two signals, the will send control frame comes on, and immediately it comes on, the TS control start frame also turns on. So the TS control start frame, this is the start of the frame transmission. So how does this turn on? So this is how the will send control frame comes on. So once this will send control frame comes on, to turn it off means at the end of the transmission of this control frame, this will send control frame goes off. So to turn this off, we have to turn on the TS control end frame, which is this, the control end. So whenever the TS control end frame comes on, it means the transmission of the control frame has ended. Therefore this will send control frame is going to turn off. So whenever it turns off, another signal that comes on is the TS control start frame. This is the start of the transmission of this control frame. Towards the ending of this circuit, we are going to see the content of this control frame here. So this is the content of the control frame. I'm going to show you how we drive this frame itself. So but these are the signal that needs to be turned on or off before you are able to send this control frame. So this TS control start frame, how do we turn it on? So first of all, these are there are three conditions to turn that on. Also three conditions here, so let's see them one after another. So the first one says, let's see this first one. The first one has this huge a lot of conditions here in this OR gate. One says TS done in. TS done in is the same as the TS done when we were discussing the transmitter model earlier. TS done, it means that data transmission has ended. Probably the transmitter was sending a data already while it was receiving equally. So once the data is done, it's no longer transmitting. Therefore let's start transmitting the control frame. So whenever TS done is asserted, the TS control start frame can turn on. Or this is another one, TS abort in. So once the TS abort in, that is abort, whenever there's a reason to abort the current transmission, maybe there was an underrun or a collision, the current transmission that the receiver's transmitter was handling has been aborted, or maybe it has stopped transmitting. Therefore there's chance for us to send this control frame. And then other conditions, there's this other one. Okay, TS use data out detected. Okay, we will see it here again in TS use data out. TS use data out and this TS use data out detected are almost the same. When the TS use data out comes on, this TS use data out detected also comes on. So all of them, the two signal has to be off. They have to be negated. They have to be off. So what is TS use data out? TS use data out means that the transmitter is currently transmitting. So what turns this TS, what makes it to come on? It comes on whenever we are about to enter the state data and we are not transmitting a control frame. I'm going to show you how we drive this in our next in our Mac control sub-circuit. Whenever you are transmitting data, that is, if you are about to enter the state data FSM, the fixed state machine of the state data, and you are not transmitting this control data, TS fuse data out comes on. We already know when we are talking about the transmitter module that TS fuse data comes on whenever you are about to enter the state data. Let me show you about TS fuse data. When you're about to enter transmission, let me check. Yes, so this is it here, TS fuse data. It comes on whenever you are about to enter this start data in your transmission. TS fuse data comes on. But the TS fuse data out we saw here also means that control mux is not on. This is a control mux here. We are going to talk about it briefly. So whenever the TS fuse data is on and this control mux is not on, this TS fuse data out turns on. It tells the receiver's transmitter that you are currently transmitting data. So that's what TS fuse data means. So it means it has to be off for you to send this TS control frame here. So then the last condition, which is okay, this one here, so means that your will send control frame must be on. That is it. Once your will send control frame is on, then this one can equally come on with other conditions attached to it. Then the TS control end frame. TS control end frame means you've reached the end of data transmission, that you are no longer sending control frame. You are done sending control frame. It turns off. So I'm going to show you how it turns off down here, the signal that enables it. This is a byte counter here also. So at the end of data transmission, this is a counter. So when it counts 22 in hexadecimal, let's see, 22, okay, we've done it already. It means 32, 34. The 34th bit, this signal comes on. It shows that you sent 32 data. Your control signal, you sent 32 data already. That is part of the things that turn off this control end frame. I'm going to show you the byte counter that counts this. So when you've counted up to 32 in binary, this TS control, it shows that you sent all your control frame, so it goes off. So let me see. So I don't know, I wish I can manipulate it so that it turns on immediately. So you see that whenever this control end frame turns on, everything about the control transmission is going to end immediately. Then we have this control mux. From the name control multiplexer, it chooses between what are we going to transmit. Are we going to transmit the control frame, or are we transmitting normal data transmission? If it comes on, it means we are transmitting the control frame. So for every set of transmission here, this once you see that the control mux is on, it means it's control frame transmission. Control frame transmission. So let's see how it comes on and off. So to turn it on, let's see, this is the AND gate that turns on the control mux. So for this control mux to turn on, the first signal says this TS use data out must be off. We've talked about it already. It means that the transmitter is currently transmitting data, and then also your will send control frame must be on. So will send control frame is the beginning of the control frame data transmission, and the state of the data transmission, the state which the transmitter stays while transmitting control frame is the control mux. So this will send control frame initiates it, and it now stays in this control mux. So control mux means that our data transmission that we have selected this control frame to be transmitted, not just our normal data transmission. So this is sending control frame, means is in the process of sending the control frame. So the same thing, let's see what turns on this sending control frame. So this first AND gate is the same. Your send control frame is on, and where is it? The last one, that TS control start frame. So log TS done. This one comes at the end of the transmission. Then so let's talk about the counter, the byte counter. Just the way we have the normal byte counter for the transmitter, the control frame also has its own byte counter. So we see how this counter works. There are also another counter, the delay CLC enable counter 2 is here also. That is when you are sending CLC with it also. So this is the delay CLC count, just as we have it in the receiver and the transmitter, is equally the same thing here. When you have larger data size to send, so let's see how it counts and what resets is also. So this is the reset here. So this OR gate has two conditions to reset. One is that, let's see, one is the normal reset. When there is a normal reset, one, or this OR gate, this condition has to be off. That is TS control start frame. Before you turn on this TS control start frame, before it's on, you have to count the CLC count. Once it's on, it means you've entered the data transmission, or what again, any of these two conditions. It says when TS done or when TS abort. So whenever transmission is done, at the end of the transmission, which normally ends with either is done or is aborted. That is aborted when there is error, and you've ended the transmission by turning off this signal, TS control start frame. TS control start frame needs to be off. That is, you've ended the transmission and is either aborted, done, and TS start frame is off. Therefore reset this delay CLC count. So but how do we increment it? So this is the incrementer. This here is our adder that increments it by 1. But let's see what does the incrementing. Is this AND gate here? Is a three, it has a 3 input AND gate here. So the conditions for incrementing it includes 1. Let's see, TS used data in. TS used data in, I think we've talked about it. It means that you are about to enter either of the states, the state idle state data. Once you want to enter the state data, the TS used data comes on, and TS used data in means the input from that TS used data, it just comes here. That is where the signal comes from the TS used data. That's where this signal comes from. So whenever you want to enter into the state data, the proper data transmission, do these counts. It's very important. Then the next condition says, let's go up and see. Let's see. Your control mux has to be on. I told you already. Once the control mux is on, it means that you are transmitting. What you are transmitting is a control frame. So this delay CLC is for control frame transmission. So for you to count it, a control mux has to be on, and finally this has to be 0. The bit 2, let me highlight it further. This is bit 2 of the counter itself. Bit 2 of the counter, you can see it, every other bit is none. except bit 2. It says that bit 2 of this the counter has to be off. When bit 2 is off, that means it's remaining only bit 0 and bit 1. And if the counter is counting from 0, 1, 2, 3, that means it counts 4 times: 0, 1, 2, and 3. Before it counts the fifth one, which is 4, that is when the bit 2 is supposed to come on. So it means bit 2 should not come on. So long as the bit 2 is not on, it should keep counting. Therefore it counts only 0, 1, 2, 3. That is 4 counts. We've talked about it. All CLC count is 4 bytes. It counts only 4 times by convention for this our circuit design here. So that is how the delay CLC counts. Then let's talk about the main counter, which is the byte counter itself. Let's see this byte counter circuit and how it works. So remember we talked about the control end. This is what turns off our control frame transmission. Whenever this our byte counts up to 22, we checked it here. In binary is see the value here, and that's why it's 34. When it counts up to 34, and the transmission. When it counts up to 34, end the transmission. So this is the counter here that does that. Then also let's see what resets our byte counter. I found out that the resets are equally the same for both this reset here that sets it to 0 and the reset that sets the delay CLC count. So they use a common reset to reset both counters. Both counters use a common reset for resetting them. Then let's look at the control data. How do we actually get this our control data? Can we see this? This is the control data. So let's pay very good attention to this particular area, because this is where the control frame or the control data is being generated. So the major item here is this multiplexer here. This multiplexer here. This is what clocks out the different parts of the control frame section by section, and it depends on the bit counter. This is the bit counter signal that's coming in. This signal, this multiplexer signal, let me show you. This multiplexer signal comes from the bit counter. So as the bit counter increases, this multiplexer clocks out different parts of the control frame byte by byte. It will be sending out the different parts of this control frame. So this is what the typical control frame looks like. It starts with 1, the destination address. I'm going to attach in the reference of this tutorial the reference projectfpga.com/reference, the course material for this tutorial. So you see this there. It starts with a 6-byte destination address, 6-byte source address, 2-byte length, opcode, pulse timer value. So this pulse timer value is this TX pulse TV. This is a transmitter pulse timer value. That is it. It's 2 bytes, 16-bit pulse timer value. So this is where you give the size of the timer, how long is going to pause before transmitting again. Your transmitter is telling the other transmitter that you should pause, that your receiver is busy. You should pause for a given amount of time. The time is given in this pulse TV. How long is going to wait before starting again. Then the reserve and the CLC, that is your CLC here. So and that's why you have this delay CLC in case you want to add more frames here. Maybe you want to add something here, so it should not exceed 4 bytes. You can add something at the beginning, whatever you want to add, so that the CLC counting will delay 4 bytes before here. So that's that. So let's see how each of these sections are being sent. So first of all, when the byte count is 0, that is, let's see this. Wait. So now look at this particular section. What actually went down here? This is a wire splitter here. There's a splitter here, and the top says bit 5 went to the top. Only bit 5. The topmost bit of this the topmost bit went here, went up, while this remaining 0 to 4 came down. That is, 0 to 4 is what actually went into this multiplexer here. So what it does is that whenever the bit gets to the highest, it turns this multiplexer on, and this multiplexer switches between everything here and your TS Plus TV. I'll still come to that actually, but let's just keep looking. I will explain it a bit further. What actually happens here is this multiplexer, this is another multiplexer here. So this says at the initial beginning of the byte count, at when the byte count is 00, because by 0 of the byte counter went into here. So when it's telling it, when it's 0, this is supposed to clock out. The input at this 0 is supposed to clock out. So it's now telling it, if this means delay CLC is enabled. If it's not enabled, then it should turn this multiplexer on, and if this multiplexer is on, the first byte to be sent is 000. Else, if delay CLC is enabled and watch here, let's watch closely here. This is bit 0 and 1. If the two of them are 1 1, that is at the end of the counting of the delay CLC enabled. Remember, our delay CLC counts 0, 1, 2, and 3, and 3 is 1 1. So it's telling it if it has finished counting, that is, here it means 1 1. That is the signal that went in here, and delay CLC is enabled. Turn this multiplexer on and send what? 0 0. Else take 0. So what it's saying is that, what this is saying that is, during CLC counting, it should send 0 0. Immediately after CLC counting, send 0 1. So remember, we have the first 6 bits as what? From this diagram, the first 6 bits is the destination address or reserved multicast. That is, if the transmitter that was sending the bit is a multicast, is sending to a multicast address, it should send back to them. Or if there's a destination address, it should send to that destination address. So this 6 bytes of data is actually the multicast. Let's see this 6 bytes of data. See the 6 here. So that multicast is 0180 C2 000001. That's in hexadecimal, so you can likewise convert it to binary and see what it entails. So this first 6 bytes, this is it here. This is the first 6 bytes here. That represents the multicast, or assuming you have a destination address, you can equally fix it here. Then the next is the source address. This is the source address, another 6 bytes. Sorry. So that represents our MAC address, which is in our register. This is our MAC address. The MAC address is actually a single MAC address, but LogiSIM does not have an input that is up to 48. So I actually divided it into two 24 and 24, but our MAC address should be 1, and it's actually another 6 bytes. So this is the 6 bytes here again. Then the next is the length, which is 2 bytes. The length is usually 8808. From convention, you will see more when you go to the code and read the file associated with this. I'm going to attach it to at the reference of this tutorial. Then also you have the opcode, which is 2 bytes. That is the operation code. That is the once the receiver receives this opcode 0001, it knows that is a pause 001. Then after that is this pause timer value. This pause timer value, this is it here, pause transmitter pause timer value. That's the meaning of this TS pause TV, transmitter pause timer value. So it's 2 bytes, which is 16. So how does this do that? So hey, sorry, what the fuck have I done? So what happens here? How is our transmitter able to add this pause TV, this TS pause timer value? It took the first 5 bytes here, then the last one, which is supposed to complete this multiplexer here, and is meant to have this pause TV here, is what is actually included in this multiplexer here. Let me explain. Let me try and explain more. What he's trying to say is whenever the MSB, the topmost bit, comes on, it's supposed to be here. The next bit that is supposed to turn on is the MSB, which comes here. Instead of being part of this multiplexer here and turning on this TS pause TV that is supposed to be here, it went to this multiplexer instead. So whenever it turns on, it takes this TS pause TV. Whenever it's 1, the TS pause TV here turns on. If it's 0, it means it's taken from here. I hope you understand this. But in actual sense, after this opcode, which is this last 2 bytes, the next is the pause timer value, which is meant to be here. But instead, it went to this next multiplexer here, because the bit that is supposed to turn it on, which is the MSB, the 5th bit, turned this multiplexer on. So as soon as I increased it, I could have increased it. So the reason I didn't include this TS pause TV at the end of this place is because Logisim does not take a select bit cannot be more than 5. So but in actual sense, the TS pause TV is supposed to be included here because that's what comes after this opcode. After opcode, you get the TS pause timer value, the reserved, and the CLC. They are all meant to be here. But Logisim, the maximum select bit for a multiplexer is 5. So I know we have 6 bits, so I decided to use a different multiplexer altogether to multiplex this T pause TV here. So that's that. Then also this video is already very long. I'm thinking of cutting it, but I'll cut it very soon. We're almost done. Then again, let's watch here this point. This wire splitter here took the LSB, which is bit 0. We can see that bit 0 here, and turns on our control data multiplexer, the one that takes the control data multiplexer once. What is doing here is that it skips 1 clock cycle and takes only 1 clock cycle, because when the byte counter is counting, it's counting 0, 1. The LSB is always counting 0, 1, 0, 1. Like we have 5 bytes and we have the LSB here. These are the upper bars. If this is the LSB, doing whatever counting you are counting is always counting 0 1 0 1 0 1 0 1. So here we are skipping one of the counts because this multiplexer itself didn't include some counts here. You see, some of them were tied together. They didn't have any value. They didn't have any value. So that's why here you can see that we will only turn this multiplexer on to accept this control data. Only one clock cycle you skip one clock cycle you skip one. So that is why here we didn't use all the pins of the multiplexer. Not all the pins of the multiplexer was used. So there's a reason for that. So the major reason for that is so that when we are transmitting the nibble, you know, we send nibble by nibble. The nibble will be able to send 4 bits at a time. Then while it's off, it's going to send the remaining 4 bits. So that is the reason why it sends this multiplexer updates this control data. One clock cycle it skips one, another clock cycle it skips one clock cycle it skips one. So that is what basically this circuitry here is doing. It takes the LSB of our byte counter, which we know already goes on and off 0 and 1 0 and 1. No matter what value is counting, it's always going 0 and 1 0 and 1. And it actually uses this NOT gate because it doesn't want to count 0. It wants to count it when it's 1. So the first count 0 doesn't take anything. Then the next count 1. At that point, it has already counted here. So it has 2 nibbles at that time. So whenever is 1 here, it has already taken 2 nibbles. So those 2 nibbles will join together. Assuming this NOT gate is not here, whenever is 0, when this multiplexer is going to come on, it's going to have only 1 nibble. So it delays it by using this NOT gate. So whenever it's 1, it delays. Then the next time there are already 2 nibbles at a time. So that is how we get this control data. Then when we are in the Mac control model, we are going to see how our control mux really works. At this point, let me end this simulation. We are going to see why we call this control multiplexer, how it does the multiplexing. So that is that. Subscribe to my channel, go through the tutorial on the website, and you understand more on what you've just done. Thank you.